The morning of July 24, 1943, west of Truk Lagoon, Caroline Islands, tropical Pacific, Lieutenant Commander Lawrence Randall Daspit stood hunched over the periscope of USS Tinosa, watching the largest prize any American submarine commander could hope to find steaming directly toward his position. The whale factory ship Tonan Maru Number Three, 19,250 tons, converted to an oil tanker carrying precious fuel from Palau to Truk. No escort, no zigzag pattern, making 13 knots on a predictable easterly course. Intelligence from codebreakers at Pearl Harbor had placed her exactly where she should be, and Tinosa sat waiting in her path like a predator at a waterhole. Daspit had every reason for confidence. His submarine carried 15 Mark 14 torpedoes, each weapon representing the pinnacle of American naval ordnance engineering, 3,000 pounds of precision machinery, 21 feet of streamlined steel containing 680 pounds of Torpex explosive, capable of blowing a hole 15 feet across in any ship's hull, powered by superheated steam generated from burning alcohol and compressed air. The Mark 14 could race through the water at 46 knots for 9,000 yards. Its revolutionary Mark 6 exploder combined two detonation methods: a magnetic influence feature designed to sense a ship's steel hull and detonate the warhead underneath the keel, where no armor protected the vulnerable bottom plates; a backup contact exploder that would trigger if the torpedo struck the target's side directly. The Bureau of Ordnance assured submarine commanders these were the most sophisticated anti-ship weapons in any Navy's arsenal. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. At 05:55 hours, Tinosa closed to 4,000 yards and Daspit gave the order. 4. The torpedoes left their tubes in sequence, their wakes drawing straight white lines across the calm Pacific surface toward the tanker's massive hull. The sonar operator heard 4 distinct metallic thuds through his headphones, 4 solid hits against steel plate. Daspit waited for the towering columns of water, the rumbling concussion through Tinosa's hull, the satisfying sight of Tonan Maru's plates buckling as high explosive tore through her cargo holds. Nothing happened. The tanker turned away and increased speed. Her radio began transmitting distress signals. Daspit surfaced Tinosa and began pursuit with diesel engines. Through the long tropical night, the submarine chased the wounded tanker, closing the distance as darkness gave way to pale dawn light. By 0900 hours, Daspit had positioned his boat for another attack approach. His torpedoman had personally inspected every remaining weapon in the tubes and reload racks. Each Mark 14 checked out perfectly. Every mechanism tested within specifications. This time, Daspit fired from the starboard quarter, angling his shot to strike Tonan Maru's engine room. 2 torpedoes launched, both hit, both exploded. The muted thunder echoed through Tinosa's pressure hull, and the crew cheered. Black smoke billowed from the tanker's midships section. Her engines stopped. The vessel coasted to a dead stop, listing to port, settling slightly by the stern. Daspit had done everything correctly. The massive ship sat helpless, a stationary target presenting her full length to Tinosa's remaining torpedoes. No destroyer escort approached, no aircraft appeared overhead, just open ocean, clear weather, and a 19,000-ton enemy vessel waiting to be sent to the bottom. This was the textbook situation every submarine commander dreamed about. Perfect firing position, unlimited time to aim, a target that could not maneuver or fight back. At 0930, Daspit maneuvered to Tonan Maru's port side, 875 yards off her beam. Precisely 90 degrees, the ideal attack angle that training had drilled into every submarine officer. From this position, a single Mark 14 with its 680 pounds of Torpex should tear a devastating hole below the waterline. 2 or 3 hits would flood enough compartments to sink even a ship this size. Daspit fired 1 torpedo. The wake ran straight and true, reaching out across the flat water to touch the tanker's flank. The weapon struck with an audible thump that carried across the distance. No explosion, just a tall plume of white water where the torpedo made contact, then sank. This was nothing new to the American submarine fleet. Reports of torpedo failures had become routine. Daspit fired again, same result, a hit, no detonation. He fired a third torpedo, another direct strike, another dud. The crew in Tinosa's torpedo room worked frantically, pulling the remaining weapons from their racks, examining firing pins, checking depth settings, verifying every component. Everything tested perfectly. The torpedoes were functioning exactly as designed. Daspit ordered another shot. The fourth torpedo since Tonan Maru had stopped running hit squarely amidships. Nothing. A fifth weapon struck near the stern, then appeared to turn 90 degrees and leap completely out of the water, about 100 feet behind the tanker, before sinking again. Daspit would later write in his patrol report, "I find it hard to convince myself that I saw this." The sixth torpedo hit. No explosion. The seventh. Nothing. The 8th, 9th, 10th, 11th torpedoes all ran true. All struck their target with enough force that Tonan Maru's crew fired back with machine guns and 4-inch deck guns, aiming at the torpedo wakes to locate Tinosa's periscope. Every hit registered as a metallic clang through the submarine's sonar equipment. Every impact failed to detonate. By 10:48, Daspit had fired 11 torpedoes at point-blank range against a stationary target in ideal conditions. 11 confirmed hits. 11 duds. A Japanese destroyer finally appeared on the horizon, charging toward the scene with white water curling from her bow. Daspit faced a choice. He could fire his 4 remaining torpedoes, likely watch them fail like all the others, then dive to escape the approaching warship. Or he could retain evidence that something was catastrophically wrong with American torpedo design. He kept 1 torpedo unfired and took Tinosa deep as the destroyer's screws passed overhead, dropping depth charges that rumbled through the water but caused no damage. At 13:57, Tinosa surfaced to find Tonan Maru still afloat, still seaworthy enough that her crew was attempting repairs. Daspit radioed Commander Submarines Pacific, requesting another submarine be dispatched to finish what he had started. At 22:20, orders came to return to Pearl Harbor. The journey back across the Pacific gave Daspit no time to cool down. 19,000-ton tankers carrying fuel to Japanese forward bases did not appear every day. That single vessel represented months of patrol time searching vast ocean areas. Her cargo would have fueled destroyers, cruisers, and aircraft that would now continue operating against American forces. Her loss would have been a significant blow to Japan's increasingly desperate fuel situation. Instead, she limped back to Truk with 11 unexploded American torpedoes embedded in her hull or lying on the seafloor beneath where she had drifted during the attack. August 4, 1943, Submarine Base Pearl Harbor, Territory of Hawaii. Daspit brought Tinosa alongside the pier carrying that single unfired torpedo and a patrol report documenting the most comprehensive torpedo failure in American submarine operations. Rear Admiral Charles Andrews Lockwood, Commander Submarines Pacific Fleet, met him at the dock. Lockwood had been fighting the torpedo problem since June 1942, when he commanded Southwest Pacific submarines from Fremantle, Australia. A career submarine officer who had taken his first command, USS A2, in 1914, Lockwood understood the weapons his men depended on and the bureaucratic resistance preventing those weapons from being fixed. He had forced the Bureau of Ordnance to admit the Mark 14 ran 11 feet deeper than its depth setting. He had gathered evidence that the magnetic exploder detonated prematurely or not at all. He had battled Washington officials who insisted the problems lay with submarine commanders' poor approach techniques rather than defective ordnance. Lockwood took Daspit to his office and listened to the lieutenant commander describe 15 torpedoes, fired, 2 explosions, 13 duds, against a target that could not evade or defend itself effectively. Lockwood later wrote, "I expected a torrent of cuss words, damning me, the Bureau of Ordnance, the Newport torpedo station, and the base torpedo shop. I couldn't have blamed him. 19,000-ton tankers don't grow on trees." I think Dan was so furious as to be practically speechless. The single torpedo Tinosa had brought back went immediately to the submarine-based torpedo shop for complete examination. Technicians disassembled every component, measured every clearance, tested every mechanism. Their conclusion: perfect working order, no defects found, every specification met. According to all technical standards, this torpedo should detonate exactly as designed when striking a target. The mathematics were brutally clear. In 1942, American submarines in the Pacific had fired 1,442 torpedoes and claimed to have sunk 211 ships, totaling almost 1.3 million tons. Post-war analysis of Japanese records reduced those figures to 109 ships and 418,700 tons. Less than half the claimed sinkings had actually occurred. Something was preventing American torpedoes from functioning as intended, and that something was costing the United States strategic advantage in the Pacific War. The weapon system that should have been strangling Japan's supply lines, sinking her merchant fleet, crippling her ability to move resources between captured territories and the home islands, that was failing at least 70% of the time. Submarine commanders were risking their lives and their crews' lives to reach attack positions, only to watch their weapons strike targets without exploding. But the Mark 14's problems were not unique to American torpedoes. Every navy that entered the Second World War faced torpedo reliability challenges. The difference lay in how those navies recognized problems, conducted testing, and implemented solutions. The story of American torpedo failures during 1942 and 1943 reveals more than just technical defects in one weapon system. It exposes the dangerous gap between theoretical perfection pursued in isolation and practical reliability achieved through realistic testing. Understanding what went wrong with American torpedoes requires understanding what went right with Japanese torpedo development, and why two industrial powers pursuing similar goals in similar timeframes produced weapons with dramatically different operational outcomes. The Mark 14 torpedo development began in January 1931. The Navy allocated $143,000 for its design and testing. This budget reflected Depression-era austerity and the reality that torpedoes were extraordinarily expensive weapons. At $10,000 each in 1942 currency, approximately $180,000 today, a single Mark 14 cost more than a new house. The Bureau of Ordnance, responsible for all naval weapons development and production, faced pressure to minimize costs while creating a weapon superior to its predecessor, the Mark 10 torpedo that had served since World War I. The Mark 14 promised improvements in every category: longer range, higher speed, larger warhead, revolutionary dual-mode exploder that could detonate either magnetically beneath a target's keel or on contact with the hull. The magnetic influence exploder, designated Mark 6, represented the most sophisticated component. Based on German magnetic pistol designs from World War I and refined through theoretical calculations, the Mark 6 aimed to solve the fundamental problem of underwater warfare. Hitting a ship's armored belt with a contact weapon might cause damage but rarely guaranteed a kill. A heavy cruiser could survive multiple torpedo hits if they struck above or at the waterline, where armor protection concentrated and watertight compartments could contain flooding. But every ship was vulnerable below its keel, where water pressure from an explosion would lift thousands of tons of steel and crack the hull like an eggshell. A magnetic exploder that detonated underneath the target promised single-shot kills against even the largest warships. Development of the Mark 6 began in the 1920s at the Naval Torpedo Station in Newport, Rhode Island. The concept was theoretically sound. Earth's magnetic field creates a roughly north-south orientation of magnetic lines of force. A large steel ship distorts that field, creating a magnetic anomaly that specialized sensors could detect. As a torpedo passed underneath a target, the change in magnetic field strength would trigger the exploder, detonating the warhead at the optimal position to break the ship's back. German U-boats had achieved some success with magnetic exploders in World War I, though reliability remained inconsistent. British scientists were also working on magnetic influence designs. The Americans intended to perfect what others had merely attempted. The problem was cost. testing torpedoes required, firing them at actual targets with live warheads to verify detonation reliability. Every test meant destroying a $10,000 weapon and potentially damaging or sinking a target vessel that the Navy might want to preserve for other purposes. In the budget-constrained 1930s, the Bureau of Ordnance decided that minimal testing would suffice. Theory and calculations should accurately predict performance. If the Mark VI worked correctly in controlled conditions, it should work correctly in combat. Only one test firing of the magnetic exploder occurred before the Mark XIV entered production. May 1926. The target was a derelict submarine. 2 Mark XIV torpedoes were fired with magnetic exploders. One ran under the target and failed to detonate. The second exploded and sank the submarine. 50% success rate. The Bureau of Ordnance declared the test satisfactory and approved the Mark VI for fleet use in 1934. No further testing was conducted. The contact backup exploder posed equally complex challenges. When a torpedo travelling at 46 knots struck a ship's hull, enormous forces were unleashed. The initial deceleration equaled approximately 500 times the force of gravity. That force had to be transferred precisely to a firing pin that would strike a primer cap, igniting the high-explosive warhead. The contact mechanism inherited from the earlier Mark III exploder used a firing pin oriented perpendicular to the torpedo's direction of travel. This seemed logical. As the torpedo struck the hull, the weapon would decelerate, but the firing pin's inertia would carry it forward along its guide rails to strike the detonator. The faster the torpedo travelled, the harder the pin would hit the primer. Engineers calculated the forces involved and concluded the design would function reliably across a wide range of impact angles and speeds. The depth control mechanism represented the third critical component requiring precise engineering. Submarines attacked from concealed positions underwater, firing torpedoes that had to maintain specific depths to hit targets at their waterlines or pass underneath for magnetic detonation. A pressure sensor measured water pressure, which increases with depth, and adjusted control surfaces to maintain the torpedo's preset running depth. The sensor location and calibration determined whether the weapon ran at 10 feet as intended or passed harmlessly underneath its target at 25 feet. During development, the Bureau of Ordnance tested the Mark XIV's depth control using exercise warheads filled with water instead of high explosive. This allowed the torpedoes to be recovered and reused, reducing testing costs. The exercise heads weighed less than combat warheads, filled with Torpex. The Bureau accounted for this weight difference in their calculations and concluded the torpedo would maintain proper depth with either configuration. Testing protocols reflected the Bureau's confidence in mathematical modelling over empirical verification. Engineers could calculate hydrodynamic forces, predict stress loads, and model component behaviour using established physics principles. Extensive field testing seemed unnecessary when theory provided clear answers. This approach worked well for many naval weapons systems. Artillery shells followed ballistic trajectories that mathematics described accurately. Armour penetration could be calculated based on projectile velocity, angle of impact, and plate thickness. But torpedoes operated in a more complex environment than projectiles flying through air. Water density, temperature, salinity, and current all affected performance. The torpedo's own motion through water created pressure gradients that theory approximated but could not fully capture without extensive real-world testing. Japanese torpedo development followed a fundamentally different path. The Imperial Japanese Navy understood that mathematical theory alone could not guarantee weapon reliability. Their approach emphasized extensive live-fire testing against actual target ships, meticulous documentation of results, and iterative refinement based on observed performance rather than predicted behavior. This difference in development philosophy would prove decisive when submarines and surface ships began firing torpedoes in combat conditions. Japan's geographical and strategic position drove their torpedo development priorities. The Washington Naval Treaty of 1922 limited capital ship construction using a ratio of 5 for the United States and Britain, 5 for the United States and Britain again, and 3 for Japan. This meant Japan would enter any Pacific conflict with fewer battleships than America could deploy. Japanese naval planners needed force multipliers that would allow smaller vessels like destroyers and cruisers to inflict disproportionate damage on a superior enemy fleet. Torpedoes represented that force multiplier. A destroyer costing a fraction of a battleship's price could carry 8 or 12 torpedoes, each capable of crippling or sinking even the largest warship. If Japanese destroyers and cruisers could launch massive torpedo salvos at night, approaching American battle lines under cover of darkness and using superior optics instead of radar, they might sink enough capital ships to achieve parity before the climactic daylight engagement. This strategy required torpedoes that worked every single time. No duds, no prematures, no depth control failures. Perfect reliability under combat conditions. To achieve that reliability, Japan invested heavily in torpedo development throughout the 1920s and 30s, accepting no shortcuts and conducting extensive realistic testing despite the costs involved. The result was the Type 93 torpedo, called Long Lance by American forces after the war. 24 inches in diameter, almost 30 feet, long, weighing 3 tons, armed with a 1,080-pound warhead that was 50% larger than any other Navy's torpedo warheads. Most remarkably, the Type 93 used pure oxygen instead of compressed air as its oxidizer, enabling it to achieve ranges and speeds that seemed impossible according to Western calculations. Compressed air is only 21% oxygen and 78% nitrogen. The nitrogen contributes nothing to combustion and creates a visible bubble trail that reveals the torpedo's path. Pure oxygen provides nearly 5 times as much oxidizer in the same tank volume, dramatically increasing range and eliminating the telltale wake that allowed targets to evade. At 35 knots, the Type 93 could reach 22 nautical miles. At 50 knots, 12 nautical miles. American torpedoes typically operated at ranges under 6 nautical miles. Developing oxygen torpedoes required overcoming extraordinary technical challenges. Pure oxygen is violently reactive. Any contamination, any sharp bend in the fuel lines, any rough surface that could create friction and heat might cause spontaneous explosion. Japan and Britain had both experimented with oxygen torpedoes in the early 1920s. Both navies suffered fatal accidents during testing. Britain abandoned oxygen propulsion as too dangerous. Japan persisted, accepting the risks and learning from each failure. Engineers eliminated sharp turns in oxygen tubing and developed specialized cleaning procedures using strong alkali solutions. They solved the detonation problem when oxygen and kerosene first mixed by starting the engine with compressed air from a separate tank, then gradually switching to pure oxygen after combustion stabilized. Testing took over a decade, from the early 1920s until the Type 93 achieved fleet service in 1935, but the result was a weapon that exceeded all competitors. The Type 93s. The warhead exploder was deliberately simple and robust. Japanese engineers rejected magnetic influence designs as unnecessarily complicated and prone to premature detonation from electromagnetic interference or variations in Earth's magnetic field at different latitudes. They used a straightforward contact exploder that triggered mechanically when the torpedo struck its target. This design philosophy prioritized reliability over theoretical sophistication. The contact mechanism would not achieve under the keel explosions that might sink a ship with a single hit, but it would detonate consistently when striking a hull, and consistent detonation mattered more than theoretical maximum efficiency. If hitting a cruiser's side required 3 torpedoes instead of 1 perfect under-keel shot, Japanese destroyers carried enough weapons to fire 3 torpedoes per target. Testing verified this reliability through methods that would have been considered extravagant waste by American standards. The Imperial Japanese Navy fired Type 93 torpedoes at the cliffs of Izu-Oshima Island, south of Tokyo Bay, to verify depth control with brutal directness. Torpedoes that maintained proper depth would strike the cliff face at the preset depth. Any deviation showed immediately in the impact location on the cliff. Later, aging hulks became test targets. Japanese technicians fired live torpedoes with full warheads at actual ships to verify that the exploders functioned under real combat conditions. This destroyed expensive weapons and target vessels, but it guaranteed that torpedoes issued to the fleet would work when submarine and destroyer commanders needed them. The testing culture extended to personnel training. Torpedo maintenance specialists in the Imperial Japanese Navy received meticulous instruction in proper handling, storage, and pre-launch preparation. Oxygen torpedoes required careful management. Improper procedures could cause catastrophic accidents, but properly contained and carefully launched, the Type 93 proved remarkably safe and extraordinarily reliable. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By the time war began in December 1941, Japan possessed approximately 2,500 Type 93 torpedoes and sufficient industrial capacity to produce more as needed. American submarines and surface ships carried Mark 14 and Mark 15 torpedoes that looked impressive on paper but had never been tested adequately in realistic conditions. The contrast became apparent within days of Pearl Harbor. December 14, 1941, 1 week after the attack on Pearl Harbor, Philippine waters. USS Seawolf encountered a Japanese freighter and fired 8 Mark 14 torpedoes. 7 missed. 1 hit the target squarely but failed to explode. So began a litany of failures that would plague American submarine operations for nearly 2 years. Submarine commanders attacked Japanese convoys, achieved perfect firing positions, launched torpedoes that struck their targets with audible metallic clangs, then watched helplessly as the enemy vessels steamed away undamaged. The first 3 months of war saw 97 torpedoes fired at Japanese shipping. 3 ships sank. Submarine skippers reported torpedoes that appeared to pass underneath targets without detonating, suggesting they ran too deep. Others reported explosions occurring prematurely before the weapons reached their targets, indicating magnetic exploder malfunctions. Some torpedoes struck hulls but failed to detonate, clearly showing contact exploder problems. And occasionally, torpedoes ran in circles, returning toward the firing submarine in the most terrifying malfunction possible. Each type of failure masked other problems. If a torpedo ran too deep, it passed underneath the target without triggering either the magnetic or contact exploder. Fixing the depth problem revealed magnetic exploder failures. Deactivating the magnetic exploder exposed contact exploder defects. Like peeling an onion, each layer revealed another flaw. Lieutenant Commander Frederick Warder, commanding USS Seawolf, experienced the full range of failures during his first 6 patrols. His submarine fired at Japanese warships and transports repeatedly, achieving hits that should have sent enemy vessels to the bottom, but instead produced only frustration. During the 7th patrol, Warder conducted his own comparative test. Finding an 8,000-ton Japanese transport anchored in Talomo Bay, Philippines, with no current or tide affecting the shot, he fired 4 Mark 14 torpedoes from 1,400 yards. The first, set to run at 18 feet, passed under the transport and exploded on the beach beyond. The second, set at 8 feet, appeared to detonate against the transport's side but caused minimal damage. The third and fourth, set at 4 feet, hit but failed to explode. Japanese shore batteries opened fire on Seawolf's periscope. Warder withdrew, reloaded his tubes with older Mark 10 torpedoes from World War I, and attacked again. Both Mark 10s exploded against the transport's hull. The ship sank. Warder filed a detailed report explaining that Mark 14 torpedoes were defective. His superiors at Pearl Harbor blamed his approach technique. The Bureau of Ordnance rejected all complaints about torpedo performance throughout 1942. Buord insisted the weapons met specifications and functioned as designed. Problems must result from improper submarine trim, incorrect approach angles, inadequate crew training, or poor maintenance procedures. The Bureau had developed these torpedoes using sound engineering principles and rigorous theoretical analysis. Submarine commanders in the field could not possibly understand the complex physics involved. If torpedoes failed, the fault lay with the operators. not the design. This institutional arrogance reflected the Bureau's semi-autonomous power structure. Even Admiral Ernest King, who held the unprecedented combined positions of Commander-in-Chief U.S. Fleet and Chief of Naval Operations, lacked direct authority over the Bureau of Ordnance. Naval bureaus operated as independent fiefdoms, answerable primarily to themselves. Challenging Bureau's technical conclusions meant challenging an institution that considered itself the final authority on all ordnance matters. Rear Admiral Charles Lockwood was not intimidated by institutional power. When he arrived in Fremantle, Australia, in May 1942 as Commander Submarines Southwest Pacific, he found himself commanding boats whose crews had lost confidence in their primary weapon. Submarine commanders were firing torpedoes they suspected would fail, putting themselves and their crews at risk in attack approaches that might accomplish nothing. Lockwood read patrol reports describing the same failures repeatedly: torpedoes running deep, torpedoes exploding prematurely, torpedoes hitting targets without detonating. The pattern was too consistent to blame on operator error. Something was fundamentally wrong with the Mark 14, and Lockwood intended to prove it despite Bureau's resistance. June 20, 1942. Frenchman Bay, Albany, Western Australia. Lockwood arranged what should have been a simple test. A large fishing net was suspended vertically in the water at a known depth. USS Skipjack, commanded by Jim Coe, fired a single torpedo with an exercise head, set to run at 10 feet depth. The torpedo tore through the net at 25 feet, 15 feet deeper than its setting. The next day, submarines fired 2 more torpedoes with similar results. One set at 10 feet pierced the net at 18 feet, another set to run on the surface went through at 11 feet. The torpedoes consistently ran 11 feet deeper than their depth settings. This single test, costing 3 exercise torpedoes and 1 damaged fishing net, proved what 800 combat torpedoes fired in the war's first 6 months had suggested. The Mark 14's depth control was defective. Lockwood reported his findings to the Bureau of Ordnance. Bureau rejected the test as invalid. The fishing net method was insufficiently precise. Water conditions in Australia might differ from conditions where the torpedoes would be used. The exercise heads used in testing weighed less than combat warheads, which might affect results. Lockwood repeated the tests with greater care, documenting every variable. Same results. The Bureau quibbled for more than a month before finally admitting the Mark 14 ran an average of 10 feet deeper than set. They recommended fleet units make appropriate depth adjustments. Admiral Ernest King, informed of Lockwood's tests, ordered Bureau to conduct their own verification. In August 1942, the Bureau completed tests at Newport and formally declared the Mark 14 ran 11 feet deeper than set. The root cause was embarrassingly simple. When Bureau increased the warhead size during development, making the torpedo heavier, they failed to recalibrate the depth control mechanism. Worse, they had moved the pressure sensor from the torpedo's nose to near its tail, where hydrodynamic effects caused lower pressure readings as the weapon sped through water. Lower pressure indicated shallower depth, so the automatic control drove the torpedo deeper to compensate. This created a feedback loop, guaranteeing the weapon would run far below its intended depth. Dynamic testing using exercise heads with depth recorders would have revealed this problem immediately. Such tests were never conducted because they cost money, and the Bureau trusted its calculations. The calculations were wrong. By August 1942, with depth control problems acknowledged and corrected, submarine commanders expected torpedo performance to improve. It did not. Fixing the depth problem merely exposed the next layer of defects. Torpedoes now struck targets at the correct depth but exploded prematurely or failed to detonate at all. The magnetic exploder, which had seemed so promising in theory, proved catastrophically unreliable in practice. Earth's magnetic field varies significantly depending on latitude and local geological conditions. The Mark 6 exploder had been tested only near Newport, Rhode Island, where magnetic field strength differed substantially from the tropical Pacific. In the warm waters where submarines operated against Japanese shipping, The magnetic trigger often detonated torpedoes 50 to 75 yards before they reached their targets. These premature explosions occurred close enough that submarine commanders watching through periscopes might believe they had achieved hits, but far enough from the hull that damage was minimal or non-existent. Japanese radio intercepts, decoded by American intelligence, reported these prematures. Enemy ships described being near-missed by explosions that caused no serious damage. Other magnetic exploder failures resulted from electrical problems. The Mark VI's generator used brush riggings that proved inadequate. Leaking gaskets allowed seawater to enter the mechanism. If a torpedo was still turning to establish its course when the warhead armed, or if depth had not stabilized, the magnetic field changes during these maneuvers could trigger premature detonation. The system was so sensitive that even normal variations in Earth's magnetic field as the torpedo traveled could cause false triggers. What had seemed like elegant sophistication in the laboratory became a fatal flaw in operational conditions. Throughout 1942 and early 1943, submarine commanders increasingly suspected the magnetic exploder but faced resistance to deactivating it. Rear Admiral Thomas Withers at Pearl Harbor refused to authorize deactivation, arguing that torpedo shortages made it impossible to waste weapons on testing. The magnetic feature promised economy of force, potentially sinking large ships with single torpedoes if it worked correctly. Abandoning that capability seemed premature. Some commanders deactivated the magnetic exploder anyway, against orders, doctoring their patrol reports to hide what they had done. Commander Lawson Ramage on USS Trout disabled his magnetic exploders and achieved immediate success, but he faced potential court-martial for disobeying standing orders. Only after Commander Dudley Mush Morton, the submarine force's most famous skipper, returned from a May 1943 patrol, having failed to sink any ships despite perfect attack setups, did Lockwood, now Commander Submarines Pacific, accept that the Mark VI had to be deactivated. Morton's stature in the submarine community made his experience impossible to dismiss. If even Mush Morton couldn't make the magnetic exploder work, nobody could. Lockwood flew to Washington in the summer of 1943 to confront the Bureau of Ordnance directly. At the Submarine Officers' Conference, he delivered a statement that captured the submarine force's mounting frustration. If the Bureau of Ordnance can't provide us with torpedoes that will hit and explode, then for God's sake get the Bureau of Ships to design a boat hook with which we can rip the plates off the target's sides. Admiral William Spike Blandy, the Bureau Chief, accused Lockwood of trying to discredit the Bureau of Ordnance. Lockwood replied, "Well, Spike, if anything I have said will get the Bureau off its duff and get some action, I will feel that my trip has not been wasted." On June 24, 1943, Admiral Chester Nimitz, Commander-in-Chief Pacific Fleet and himself a former submariner, ordered all submarines under his command to deactivate the magnetic exploder. Rear Admiral Ralph Waldo Christie, commanding submarines in the Southwest Pacific from Australia, refused to comply. Christie had been personally involved in developing the magnetic exploder in the 1930s and could not accept that his work had failed. The boats under Christie's command continued using the defective magnetic feature, suffering continued failures while Nimitz's submarines in the Central Pacific began achieving more consistent results with contact-only detonation. Then came the Tinosa incident. Dan Daspit's 15 torpedoes, 13 duds, and 1 retained for analysis. Even with the magnetic exploder deactivated, even with depth control corrected, the Mark XIV still failed at an unacceptable rate. The problem was the contact exploder itself, the backup system that should have worked when everything else failed. Commander Charles Swede Momsen, commanding Submarine Squadron 2 at Pearl Harbor, took charge of the investigation that would finally reveal the contact exploder's fatal flaw. Momsen was a decorated officer who had overseen the rescue of USS Squalus's crew after that submarine sank off Portsmouth, New Hampshire in 1939. He was also known for speaking his mind regardless of political consequences. Lockwood trusted Momsen to find the truth. Mommsen studied charts of Hawaiian waters looking for a location where torpedoes could be fired at vertical cliff faces and recovered from sandy bottoms. The island of Kahulawe provided ideal conditions. Sheer cliffs dropped straight into deep water. Beginning August 31, 1943, Mommsen supervised live firing from USS Muskellunge. The first 2 torpedoes exploded against the cliff. The third hit, but did not detonate. That dud was carefully recovered by divers who disarmed it and brought it back to Pearl Harbor. Torpedo technicians disassembled the contact exploder mechanism and discovered guide pins that were severely bent and deformed. The physics of the failure became clear once engineers understood what they were looking at. When a 3,000-pound torpedo traveling at 46 knots struck a solid surface at 90 degrees, the impact deceleration generated forces approximately 500 times the force of gravity. That enormous force acted on the firing pin, which had to travel along guide pins to strike the primer cap and detonate the warhead. But the guide pins themselves were made of steel and subject to the same tremendous forces. At 90-degree impacts, the inertial load bent the guide pins before the firing pin could travel far enough to strike the detonator. The mechanism literally crushed itself before it could function. The firing pin, also made of steel and relatively heavy, could not overcome the friction created by bent guides and deformed mechanisms. It failed to strike the primer cap with sufficient force to cause detonation. The irony was devastating. Submarine commanders had been taught that 90-degree broadside shots represented the ideal attack geometry, maximum probability of hitting the target, shortest torpedo run time, least chance of the target maneuvering away. Training emphasized achieving that perfect perpendicular approach, but perfect approaches produced perfect failures. The contact exploder worked better at oblique angles, where impact forces distributed differently, and the mechanism had fractionally more time to function before being crushed. The 2 torpedoes that had exploded against Tonan Maru struck at angles. The 11 that failed struck nearly perpendicular. Daspit had executed textbook-perfect attacks that guaranteed his torpedoes would not detonate. Lockwood's team at Pearl Harbor conducted additional tests to verify the problem. They constructed a 90-foot crane and suspended torpedoes filled with sand instead of explosives, but fitted with live contact exploders. The weapons were dropped onto steel plates, positioned at different angles. At 90-degree impacts, 70% of the exploders failed to detonate, 70%. At 45-degree angles, the failure rate dropped to 50%. At more oblique angles, the exploders worked reliably. The interim solution was to order submarines at sea to avoid perpendicular shots and aim for glancing angles instead. This contradicted all training and tactical doctrine, but it reduced dud rates immediately. The permanent solution required redesigning the firing pin mechanism. The answer came from an unexpected source. During the Pearl Harbor attack on December 7, 1941, multiple Japanese aircraft were shot down over Oahu. American engineers examining the wreckage discovered that propeller blades were made from a lightweight aluminum alloy with exceptional strength-to-weight characteristics. The same alloy could be used to manufacture firing pins and guide components for the Mark 14 exploder. Lighter pins required less force to overcome inertia and friction. They would strike the primer caps harder and faster, even when guide pins deformed under impact stress. Pearl Harbor workshops began fabricating new firing pin assemblies using Japanese aluminum. The irony that America's most advanced naval weapon required material from downed enemy aircraft to function properly was not lost on anyone involved. By September 1943, modified Mark 14 torpedoes with corrected depth control, deactivated magnetic exploders, and redesigned contact mechanisms began reaching the fleet. The transformation was immediate and dramatic. USS Haddock conducted the first combat test of the fully corrected torpedo, sinking 2 Japanese ships with 4 hits and 0 duds. Other submarines reported similar results. The weapon that had failed 70 to 80% of the time now worked reliably. The Pacific submarine campaign that had been frustratingly ineffective through most of 1942 and 43 suddenly became devastatingly successful in late 1943 and 1944. American submarines sank 1,178 Japanese merchant vessels, totaling 5,053,000 tons, and 214 warships. They destroyed 55% of all Japanese shipping losses during the Pacific War. 52 American submarines were lost, with 374 officers and 3,131 enlisted men killed. The silent service suffered 40% of all U.S. naval casualties in the Pacific, the highest casualty rate of any American military branch, yet they achieved strategic results that fundamentally altered the war's outcome. Japan, an island nation completely dependent on imported resources, was systematically strangled by submarine blockade. Oil from the Dutch East Indies could not reach Japanese refineries. Rubber, tin, rice, and raw materials from Southeast Asia could not reach home islands. Reinforcements and supplies could not reach garrisons on isolated Pacific islands. The merchant fleet that should have sustained Japan's war effort was destroyed faster than Japanese shipyards could replace losses. But success in late 1943 and 1944 could not erase the cost of failure in 1942 and early 1943, 20 months of defective torpedoes, hundreds of patrol missions that accomplished nothing, thousands of attack opportunities wasted, submarines lost while carrying weapons that might not work if they survived to fire them. The strategic consequences were profound. If American submarines had possessed reliable torpedoes from December 1941 onward, the Pacific War might have been shortened significantly. Japanese merchant shipping losses would have begun earlier and climbed more steeply, starving the empire of resources when her industrial capacity and military forces were strongest. The Battle of Midway in June 1942 saw USS Nautilus hit a Japanese carrier with at least one torpedo that failed to explode. A functioning torpedo might have sunk that carrier before aircraft could be recovered, potentially changing the battle's outcome. Countless convoy escorts, troop transports, tankers, and warships survived torpedo attacks in 1942 that should have sent them to the bottom. The torpedo scandal's roots lay in institutional failures that transcended technical problems. The Bureau of Ordnance's refusal to conduct adequate testing, their reliance on theoretical calculations instead of empirical verification, their rejection of field reports from experienced submarine commanders, their insistence that problems must result from operator error rather than design flaws. The semi-autonomous power structure that made bureaus accountable to no one except themselves. The budget restrictions that made expensive live-fire testing seem wasteful when mathematics could predict performance. The assumption that American engineering excellence guaranteed weapons superiority without need for the extensive testing that other navies considered essential. Every one of these factors contributed to creating and perpetuating failures that cost lives, wasted resources, and delayed strategic success. The contrast with Japanese torpedo development could not have been more stark. Where American engineers trusted calculations and minimized testing, Japanese engineers tested exhaustively and refined iteratively based on observed results. Where the Bureau of Ordnance fired one magnetic exploder test and declared the design satisfactory, the Imperial Japanese Navy fired hundreds of live torpedoes at cliff faces and target hulks to verify every aspect of performance. Where American development prioritized theoretical sophistication, Japanese development prioritized practical reliability. Where Buord blamed submarine commanders for failures, the Japanese Navy assumed weapons required testing until they worked perfectly under realistic combat conditions. The Type 93 represented over a decade of continuous development from the early 1920s to fleet introduction in 1935. That investment in time, resources, and realistic testing produced a weapon that functioned flawlessly when Japanese destroyers and cruisers needed it. American submariners eventually recognized what their Japanese counterparts had demonstrated throughout the war. Reliability mattered more than sophistication. A simple contact exploder that detonated every time beat a complex magnetic system that failed unpredictably. Extensive testing with expensive weapons destroyed in verification trials cost less than operational failures that wasted hundreds of combat torpedoes and squandered irreplaceable attack opportunities. Engineering excellence meant building weapons that worked under actual operational conditions, not weapons that looked impressive in theoretical calculations. The institutional arrogance that prevented the Bureau of Ordnance from acknowledging problems until overwhelming evidence forced recognition had cost America strategic advantage in the Pacific's opening years. Officers like Charles Lockwood and Swede Mommsen, who fought bureaucratic battles to fix defective weapons despite institutional resistance, saved the submarine campaign from complete failure and enabled the devastating effectiveness that characterized operations after September 1943. The post-war assessment was unambiguous. United States submarine operations in World War II succeeded brilliantly once reliable torpedoes reached the fleet. Those same submarines had been crippled for nearly 2 years by weapons that failed most of the time despite looking sophisticated on paper. Japanese surface ships and submarines carried torpedoes that worked reliably from the war's first day to its last. The Type 93 Long Lance was arguably the finest torpedo any navy fielded during World War II. Its combination of range, speed, warhead size, and absolute reliability gave Japanese destroyers and cruisers capabilities that American forces could not match until radar and superior tactics overcame the technological disadvantage. Japanese submarine torpedoes, though less impressive than the Long Lance, featured robust contact exploders that detonated consistently when striking targets. The admission that Japan had built reliability American engineers initially failed to achieve came not through captured equipment analysis, as with the German Sherman tank testing or the British magnetron examination, but through the painful experience of American submariners firing defective weapons in combat for 20 months. Every dud that struck a Japanese hull without exploding was evidence that American torpedo development had failed fundamental engineering requirements. Every premature explosion that allowed enemy ships to escape was proof that sophisticated theory, without adequate testing, produced unreliable weapons. Every depth control failure that sent torpedoes passing underneath targets demonstrated that calculations alone could not substitute for realistic verification. The evidence accumulated through 1,442 torpedoes fired in 1942, through Lockwood's fishing net tests in Australia, through Daspit's 15 torpedoes against Tonan Maru, through Mommsen's cliff firings and drop tests at Palau. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.